shall I just press this one?
Yes.
Okay.
That's maybe the laser pointer. Maybe in the pocket, not to restrain yourself.
Okay. Yeah. Hi everyone. So I'm Liang Zhu. I am a PhD student at the University of Southern California. So I'm going to be talking about our measurement of TLS certificate revocation. It's a joint work. It's a joint work with Johanna from ICSI and Tom Heidemann from USC ISI. So here we all know that certificate is very important for current internet because we all use it for encryption and authentication. However, certificate revocation happens in the real world, and people's information and personal data can be stolen because of some certificate can be actually compromised, and also registered certificate event Heartbleed actually cause a lot of certificate compromises. So it's very important to do certificate revocation when the compromise happens. And the most common way to do that is to use OCSP, which is Online Certificate Status Protocol. So here, basically, when the client receives the server's certificate, so the client will just send a short HTTP request to just check the status of the server certificate. And at the same time, the TLS handshake can be continued, but the client application can be actually delayed in some applications. And there are also some other methods, for example, OCSP sibling and CRL. But in this paper, we only focus our measurement on OCSP. Actually, there were some concerns about OCSP. So the previous study in 2012 shows that the medium latency of OCSP is about 290 milliseconds. So it was quite slow, and we as application users, I would say, really want something like less than 100 milliseconds. And also privacy is another issue. Because OCSP servers can know all the websites the user visited. And some very important applications, for example, Google Chrome, actually disable OCSP because of these issues. So in this paper, we want to show that OCSP is actually not slow right now. So our contribution is to show OCSP latency has improved a lot, and it's actually because of the use of CDN, and OCSP is a very important protocol because many applications are actually using it. And we have some details in the following slides, and I will talk about them. So our approach combines passive and active combines passive and active measurements. So our passive measurement is done with Bro, and we capture the traffic at UC Berkeley, and so the passive measurements actually emphasizes on some very popular servers. So we also active probe some OCSP servers to just verify our measurement results. And our active probe was done from two vantage points, from USC and also UC Berkeley. So the first question we want to answer is that has OCSP been actually used at all? and or how widely it has been used. So from our measurement, we see that about it's about 90% of the IP addresses using TLS also send OSSP. So OSSP is actually widely used. And we extract the user agent field from all the HTTP requests, and we see a lot of applications are actually using OSSP right now. And also among them, there are a major portion is the web browsers and libraries and daemons. So it actually because some web browsers use their own agent to do OSSP request. For example, Firefox and Chromium Linux. However, some other some other web browsers will just use operating system functionality to do the OSSP request. So the previous work shows the OSSP latency is quite slow, and however here from our passive measurement we see that so we see that the OSSP the OSSP lookup is actually quite fast now, and we see the medium latency is about 20 milliseconds, so it's quite good. So the next question is why it is fast now. And from our data, we see that it's actually because of the use of CDN. So here we map an IP address to the reverse DNS lookup name, and we will take it as a CDN if the DNS name belongs to a well-known CDN or it has a keyword CDN in it. So from our data, we see that it's about 94% of the query traffic to certain CDNs. And here another interesting point is that actually the server, the CDN server is not the most, but there are a lot of traffic to all the CDN servers. So there are some servers are actually very popular. So here we study all the popular OSSP servers, and we see all the top 10 busiest OSSP servers all use CDNs. So the key takeaway here is the use of CDN among OSSP servers is quite common. And from the previous passive measurement, it emphasizes on some very popular servers, and it contains a lot of requests to the same popular servers. So here we want to verify our results from active probing. So here we actively probe OSSP servers of some very popular websites. From our two vantage points at USC and UC Berkeley. And also we see that the active probe shows that OSSP, the OSS latency is also quite good. And here at UC Berkeley, and we see the very the similar results to our passive measurement. So the medium latency is only about 20 milliseconds. At the USC, and we see a much lower latency. And here we did some trace route to some CDNs, and we see that it's actually because there are a few hops from USC to certain CDNs. And so here we already see that the OSSP is it's quite fast by itself. But the question is, how does OSSP slow down in TLS connections? So there are actually three kind of different implementations. So the OCSP can be performed sequentially with TLS connection. So here we define the TLS delay as the time between the client hello to the application data from the client, and a sequential OCSP can completely interrupt the TLS connections. And here we see so there is a lot of delay because of the OCSP. And also OCSP can be done in parallel with TLS connections. However, if the OCSP is slow, so it will still cause some delay in the TLS delay. So it is because the client cannot send the application data before the OCSP responses. And of course, if the OCSP is fast enough, so there will be no delay for the parallel OCSP. To further study how does OCSP slow down TLS connection, so here we have to match OCSP request to all the TLS connections because they happen in different kind of connections. So here we match them by the source IP and several unique information of certificate, and also, of course, OCSP request should happen after the certificate is actually received. So for all the matched cases, so here we plot the OCSP latency and the TLS latency, and also the ratio between of them. And we see that so the OCSP lookup is actually only 10% of the TLS delay. So it's good, and it has 10% of the TLS delay, and it has very small latency. So it's about 16 milliseconds by the medium, and so it's much smaller than the TLS delay. And here we think this small cost indicates that so if the OCSP is performed in parallel with TLS, so the cost of OCSP is actually so actually does not matter. So here we see so OCSP latency is quite good because of CDNs. So that's so how about the privacy problem? So his privacy by OCSP is a very big problem. So here we study the so all the cache time for the OCSP responses, and we see so it's about 80% of all the OCSP response can be cached for more than 1 day, and we think this long-term cache can actually limit the privacy leak. So we think the privacy is actually a secondary issue. So to conclude, and here we show that OCSP is very important protocol, and the cost of OCSP is actually it's actually acceptable because of the use of CDN, and we suggest all the application developers should use OCSP when possible, and all the CAs should also use CDNs. So with that, I would like to take some questions.
Question? Yes.
Both your traffic and your Alexa study is very CDN biased. First, does that generalize to the whole internet? And second, do you think there is a bias in the latency that it's small because of actually that sampling bias that's a bit too CDN centered?
So can you repeat your question again?
Yes, if you sample the IPv4 address space in a different way that is less Alexa or C driven, you can get a difference. So if you check low popularity Alexa top 10K or the tail of the Alexa to see, okay, these results actually still hold.
So we only check the top. So we only check the top 1,000. We do not check the tail. But we think so actually users will only so here we think most of the users will get access to the very popular website. So here we think tail might have tails might have a very long latency, but it does not matter for most of the users. So because
yeah, but that's still getting one side. So it's one university side. The question is, it's still one but this point.
Next question.
So,
Yes.
more like a clarification, you were saying that 88% of the IPv4 address using TLS also send OSCP. What does that mean? I understood it as a client side thing. Can you clarify what that means, that 88% of the IPv4 address?
So here, so we check. So here we check all the IP address for all the tails connections, and we see some OSSP requests are also from this kind of IP address. So there's correlation between the TLS and OSSP because the TLS. So there are so for a TLS connection, so the application should check the OSSP for the certificate. So here basically we show a lot of users of the TLS connections also use OSSP. So here we want to show is actually has been so here we want to show that OSSP has already been used widely.
Okay, last one. I think you were first. Yes.
So, you mentioned that because the median latency is only 20 milliseconds, because you mentioned that the median latency is only 20 milliseconds, you assumed it could be done in parallel with the completion of the TLS handshake. But have you actually observed that this latency didn't contribute to the overall latency?
So actually, we have already manually checked some TLS connections from our traffic, but we actually do not distinguish. So we actually does not distinguish between how the TLS connection from our passive measurement, but we do see that happens in the real world. So the OSSP can actually be done in parallel with TLS. So it is with TLS connections.
Okay, thank you very much again.
Thank you.